Hey, this is chapter 4.5 and 4.6. We're going to be solving square roots and complex numbers. So first, let's go over some properties of square roots. So we have the square root of a times b. This is the same thing as the square root of a times the square root of b. Therefore, when we apply this to actual numbers, we can have the square root of 18, the same thing as the square root of 9 times the square root of 2. Which, when we simplify, square root of 9 is the same thing as 3, so we have 3 root 2. Similarly, when we divide in a square root, so we have the square root of a divided by b. That's the same thing as the square root of a divided by the square root of b. And now, in real life application, we have the square root of 2 divided by 25, which simplifies to the square root of 2 over the square root of 25, which is the same thing as the square root of 2, or root 2 over 5. Next, we have rationalizing the denominator, which is a step we take. Say we have a square root in the denominator of our expression, or our problem, and we want to know what the next step is. So we've already gone from the first to the second step by doing what we just did in the previous slide, which is the division of square roots. So when we can simplify this even more, we want to know what to do with the root 2 on the bottom. So what we're going to do is multiply by root 2 on both the numerator and denominator, which in reality we can do because in reality this is the same thing as 1. Anything that has the same numerator and denominator equals 1. So after doing that, we use our properties that we just learned to simplify this. So we have the square root of 10 over, and then if you multiply a square root by itself, we get that number over 2. And this is our answer. Now we have another problem where the square root is in the denominator, this problem here, and now instead of just multiplying by 2, we need to multiply by the conjugate of the denominator, which is 7 minus root 2. So if we take the same thing and flip the plus sign to a minus sign to get our conjugate, and then we're going to multiply both the numerator and the denominator by the same thing once again, because this equals 1. So we have 3 times 7 minus root 2 over 7 plus root 2 times 7 minus root 2. And we do this so that we have a difference of squares on the bottom, rather than two addition problems multiplied by each other, which will give us too many different values on the bottom. So when we simplify this, so once we've simplified everything, we get 21 minus 3 root 2 over 47. And these steps here are really just using algebra to multiply out our difference of squares, and then we just add a bit, and then this is our final answer. So let's apply these properties to a quadratic equation. So we're going to solve this how we know how to do algebraically. So we get 3x squared equals 36, and then x squared equals 12. So we've done subtraction here, and then we did division. Next we're going to take the square root of both sides. So we have x equals, and then since we took the square root, we actually are ending up with two answers at this step. So therefore we need to have the square root of plus or minus root 12. Because if you think about it, say we have any squared number. So say we have the square root of 4. Both 2 squared equals 4 and negative 2 squared equals 4. So for every square root there are two solutions. So that's why we have the plus or minus root 12. And then we can simplify this even more. We have plus or minus 4 times the root 4 times root 3, which is 2 root 3. So in our final answer we have 2 root 3 and negative 2 root 3 because of our plus or minus. So section 4.6 is complex numbers. So we have this term here, I, and we're going to define that as the equivalent of a negative 1 by which we are taking the square root. So by that logic, squaring it will give us negative 1. So if we want to simplify, this actually should be negative 3, the square root of negative 3. If we want to simplify this, this will be I root 3. And if we square this, we will have I squared times 3, which is negative 3. So we have these two properties, and we can really transform them to get our different properties. So say we had I to the 4th, we could use what we know about I and I squared. And once again, when we're applying to actual numbers, we can do the same thing. So let's apply complex numbers to a quadratic equation. We're going to solve this algebraically first. And we get to the point at which we have a square root of a negative number. Now this is when we can use our I property. So we have plus or minus once again because we're taking a square root. And then we have I root 24. This in turn can be simplified into plus or minus 2I root 6. Because when we simplify this, we have 24 is the same thing as 4 times 6, which is the same thing as 2 root 6. And we just have an I. This, and our final answer is 2I root 6 and negative 2I root 6. So when looking at the patterns and relationships of complex numbers, remember we define complex as I. But within complex numbers, we have real and imaginary numbers. So real numbers have the form of a plus 0I, which means they're just a. So that means it's just a constant. It could be negative 1, could be 5, could be pi. All of these are real numbers. Now imaginary numbers, these are the form of a plus bi, in which b is not 0. So we could have 2 plus 3i, negative 5 plus 4i, etc. And then within imaginary numbers, we have pure imaginary numbers, and these are simply the I part. So we could have I, we could have negative 5i, etc. Next, we're going to take our complex numbers and we're going to add and subtract them. So when we're solving these problems, they're pretty simple. We just have to take 8 and 5. I should do that in a different color. 8 and 5 and solve those together, and take the i's and solve those together. So I will have in my simplified answer 8 plus 5 plus, we're going to take the constants from our I values, so we have negative 1 and 4, negative 1 plus 4, and then we're going to factor out the I, so we're just leaving the I on the end by itself. So our final answer is 13 plus 3i. Moving on to our second problem, we have a similar type of problem in which we are going to group our numbers the same way. So we can simplify this as 10 plus negative 6 minus 7i. So we're just distributing the negative sign here, plus 4i. So we have 4 minus 3i. So now we're going to be multiplying and dividing complex numbers. So let's approach the first problem as we would a FOIL problem. So if you remember what FOIL stands for, FOIL is F-O-I-L, and the F is first, O outer, I inner, L last. So when we are multiplying, we want first, so 9 times negative 4, negative 36. Outer, the two outer values, 9 times 7i is plus 63i. The inner values, so we have plus 8i, and the last value, so minus 14i squared. Next, we're going to simplify this by combining like terms, so these two values, and simplifying the I squared. So we have negative 36 plus 71i, 1i, it's supposed to be 7, minus 14 times negative 1. Sorry, it's a bit messy, but our final answer here is negative 22 plus 71i. And we can't simplify the I because it's not a squared value, so we're just going to leave it as I. Next, let's divide complex numbers. So we're going to solve this kind of similarly to how we did square root problems in division. So we're going to multiply by the conjugate of the bottom. This time the conjugate is 1 plus 4i, which is similar to square roots because we're taking the value and changing the sign, so we're going from negative to positive, and we're multiplying by the same number by the numerator and denominator, which is 1. So we're really not changing the answer, but we're simplifying it. It's another version of simplifying. So we're going to do FOIL on the top, and then we have a difference of squares on the bottom. So after we've done that, we're going to simplify the I squared on the top, combine like terms, and do the exact same thing on the bottom. So we have our final answer. Actually, we're not there yet. For this part, we have 7 plus 33i plus 20 times negative 1, 1 minus 16 times negative 1. This simplifies to negative 13 plus 33i over 17. And if we want this in standard form, which is the form of a plus bi, we can have negative 13 over 17 plus 33i over 17. Finally, we're going to plot complex numbers. So we have 3 minus 2i as our first number. So on this graph, our axes are a little different than our xy axes. Instead we have a real and imaginary. And if you remember a plus bi form, oh, that's the wrong one. We have a plus bi. The real part is the a, and the imaginary part is the I part. So it makes sense that we're going to be moving on this axis 3 spaces to the right, 1, 2, 3, and then we're moving on the imaginary axis, the I part, down 2. So we're going to plot this point here. This is our A. Then we're going to plot our B using the same method. So we're going to go left 2 spaces and up 4. So when plotting our C point, we need to realize that this is the same thing as 0 plus 3i. So we're not moving any distance on our real axis, and we're only moving on our imaginary axis. So we're moving 3 spaces up. And this is our C. Finally, for our D point, we're going moving left 4 spaces and down 3. So we have 1, 2, 3, 4, and down 3. This is our D.